Hello, I'm Dave Woolley, a retired geologist. I'm standing in front of Easter Island Store in Lynchburg, Virginia, and we'll be giving a talk on crystallography and end up being crystallography important to fasteners. And we'll start with some models. And this is a model of a cubic crystal system, and it's a representation of three equal length axes, left to right, front to back, top to bottom, that all meet at right angles. And in front are two examples of cubic crystal system minerals. This is a cubic form, axis left to right, front to back, top to bottom. This is also cubic crystal system mineral fluorite. It's a cleavage sample. Same crystal system, left to right, front to back, top to bottom. Left to right, front to back, top to bottom. All three axes equal length and at right angles. The next crystal system is tetragonal. Very similar. There's two axes that meet at right angles that are the same length, left to right, front to back, but a third axis that also meets at right angles. It's either longer or shorter. And here's a nice sample of apophyllite that shows left to right, front to back, equal length at right angle, and a longer, in this case, a longer axis at right angles, top to bottom. The next crystal system is orthorhombic. Very similar, three axes that meet at right angles, but they're different length. Left to right, front to back, top to bottom. This is a sample of andalusite that represents that change in symmetry from the apophyllite, left to right, front to back, and top to bottom. The next complexity is still similar. It's three axes, two of which meet at right angle, and a third one that is skewed. And you'll note also that there are three different lengths in the crystal systems. This is a sample of spodumene that shows that skewing from the right angle. I'll hold it this way, perhaps you can see it better. And the last obvious crystal system, that was monoclinic. The last crystal system is triclinic, in which there are three unequal length axes, none of which meet at right angles. Here's a feldspar crystal that shows everything kind of cattywampus, if you will. Now I'm going to backtrack to a crystal system that's very similar to tetragonal, and it's called hexagonal. And you'll note this time, instead of two axes that meet at right angles, there's three axes in a plane that meet at 120 degrees. At right angles to that is either a longer or a shorter axis. This is an example of a beryl crystal, which shows there's three axes in a plane that meet at right angles to, in this case, in this sample, a longer axis. There's kind of a last oddball variation of that, in which the three axes are off-centered, if you will. They still meet at 120 degrees in a plane, and the third axis, in this case, is shorter. When the axis is longer, like in the tetragonal examples over here, it's called positive, and when the odd length axis is shorter, it's called negative. This would be a positive hexagonal, and this would be a negative trigonal. Here's an example of a tourmaline crystal which well demonstrates the trigonal form. Three axes kind of off center in a plane that meet at right angles to another axis. Two more examples of the tetragonal. This is a corundum crystal with a hexagonal form, but you can probably see a triangle reflection which shows the association with the trigonal form. If I flip it over, you can see the same, but the triangle is pointed the opposite direction in this case. This is basic mineralogy to all minerals. To a faceter, however, things become quite bizarre, if you will. Light traveling in any direction through a cubic crystal system mineral travels with equal ease and goes right straight through. Light traveling in all the other crystal system, with one or two exceptions, which I'll get to in a second, light is broken up into two paths. And I want to demonstrate that on this piece of calcite. If you look straight down from the top, you'll see that there's a single dot. I'm looking down the so-called C-axis of the trigonal crystal system representation. If I rotate it, there's still just a single dot. Now, any other orientation than that, what my finger's pointing at, light is broken into two paths. And in this sample, you can see there are two dots. And when I rotate the sample, one dot stationary, that's looking down that yellow C-axis, and the other is rotating around it, and that's called an optic axis. Coming back over to the models, this is cubic. Light travels equally with equal ease in any direction. In tetragonal and hexagonal, if light travels in this direction, it has the view, if you will, of that plane of equal length axis. Any other angle, and light is broken into the two paths that I just demonstrated in calcite. In these three models that are colored black, green, and blue, there are two optic axes. There are two orientations not related to the crystal axis where light goes straight through. In all other orientations, light is broken into two paths. So this makes for a challenge for faceters who want to understand how to get the most sparkle out of a gem, and there are other considerations such as refractive index, color zoning, so on and so forth. But this completes, no it doesn't. Here I'm going to also show on this sheet of paper, these several minerals are all cubic crystal system minerals. They don't all have the same form. Here's the cube, three axes, left, right, front, back, top to bottom. Here's the octahedral, left to right, front to back, and top to bottom. And now it's difficult for me to hold, but here are several other cubic crystal system minerals of different forms. Trapezohedron, pyritohedron, which has faces that are five-sided. If I hold it correctly, there's top to bottom, left to right, front to back. Garnet is a dodecahedron. If I hold it correctly, left to right, front to back, top to bottom. And here's a combination of form, garnet, which also demonstrates that same 3 equal length axes, left to right, front to back, and top to bottom. And we want to thank the founder of this establishment, Luis Gonzalez, who's no longer with us. There was a political problem for Chile. He got his family out, moved to the United States, and opened this store. And some 30 years ago, he also founded the Lynchburg Gem and Mineral Society, which I'm also a past member. And the gentleman holding the camera today is James Tomlin, who is also the current president of the Lynchburg Gem and Mineral Society. Thank you.